Deep within the celestial canvas of Leo, a tapestry of stars woven 120 light-years from our terrestrial haven, the James Webb Space Telescope has cast its golden gaze upon a world that whispers secrets, poised to redefine the very genesis of life's chronicle across the cosmic ocean. Here, a sphere exists, veiled in an atmosphere that pulsates with the chemical breath of unseen organisms, a realm where temperature holds a steady, almost temperate embrace at 49 degcentas, 120 grad. Scientists, with a certainty that resonates like a cosmic bell tolling at 99.7%, believe they have touched the verifiable edge of another living truth. This is K2-18b, a planet not merely teeming, but thriving, perhaps even more hospitable than our blue marble, defying our ingrained assumptions of what a habitable world must be. It is a revelation born from the delicate dance of photons captured on a quiet Tuesday morning in December, encoded within the luminous streams reaching Webb's discerning eye. At Cambridge University, astrophysicist Niku Madhusudhan bore witness to this slow, deliberate unfolding. His screen presented a cosmic ballet of faint dips and rises in starlight, each undulation a fragment of an ancient narrative, a photon-born message traversing a century of interstellar void. Then, an anomaly. A chemical ghost in the machine, dimethyl sulfide. On Earth, this molecule is a signature, an exclusive testament to life, the silent industry of oceanic plankton, the microscopic architects of soil bacteria, the metabolic hum of countless invisible biota. It does not arise from the fiery exhalation of volcanoes, nor the electric etchings of lightning, nor the slow alchemy of mineral reactions. Its genesis is purely biological. The signal was not a whisper, but a resonant chord. The probability of error dwindled to less than 3 in 1,000. Madhusudhan's hands in that sacred moment trembled not from fear, but from the profound thrill of proximity to the impossible. Somewhere, across 120 light-years, a living entity was reaching out, asserting its existence within the profound silence of the cosmos. K2-18b, the source of this ethereal exhalation, traces its orbit around a diminutive red dwarf star, a stellar ember nestled within the constellation of Leo. With a mass approximately 8 times that of Earth, it possesses the gravitas to cradle a deep, extensive atmosphere, yet remains sufficiently modest to avoid the colossal embrace of a gas giant. For eons, astronomical wisdom posited such worlds as desolate, their thick hydrogen mantles and crushing gravitational fields deemed inherently inimical to the delicate spark of life. Yet, Webb's data unfurled a narrative entirely unforeseen. Beneath that dense, hydrogen-rich atmosphere, the planetary surface maintains a balmy equilibrium around 49 or 120 degrees. Warm, certainly, but crucially, gentle enough to allow for vast reservoirs of liquid water. The hydrogen itself, far from a suffocating blanket, acts as a sublime insulator, tenderly trapping heat and orchestrating its even distribution across the globe, a planetary thermodynamic marvel. Madhusudhan's dedicated team had immersed themselves in the study of K2-18b for many months, meticulously harvesting the faint starlight filtered through its atmospheric layers each time the world transited its parent star. Each transit was a new verse in an unfolding poem. First, the shimmering presence of water vapour, then the organic breath of methane, followed by the familiar exhale of carbon dioxide, a complex molecular cocktail that, in its totality, painted a portrait of dynamic balance, of an exquisitely tuned planetary metabolism, and then the unmistakable poignant reveal, dimethyl sulfide, the olfactory signature of biology itself, a scent carried across the immense void. In the austere lexicon of astronomy, true certainty is a rare and precious commodity. Most nascent discoveries emerge as tentative whispers, fragile possibilities easily eclipsed by subsequent data. But this revelation resonated with an almost unprecedented 99.7% confidence. a statistical potency usually reserved for the momentous unveilings of subatomic particles or the elusive ripples of gravitational waves. For the first time, humanity stood not in the realm of conjecture, but on the precipice of a verifiable truth. The planet's colossal atmosphere, rather than a harbinger of destruction, functions as a colossal, nurturing greenhouse, an atmospheric embrace that orchestrates a state of profound thermal equilibrium. Water, the very elixir of life, neither succumbs to freezing nor yields to boiling. It simply exists, vast, deep and immutably stable, a primordial soup on a planetary scale. Such a world, in its serene chemistry, would be a veritable Eden for the intricate processes of biogenesis. Life, once sparked, would not contend with the ceaseless battle against devastating droughts or the crushing grip of glacial winters. Evolution instead would unfurl with an uninterrupted grace, like a cosmic melody that knows no end. Its parent star, a red dwarf, burns with a soft, enduring glow, a contrast to the fiery exuberance of our sun. Small, unswervingly steady and nearly immortal, red dwarfs are the venerable elders of the stellar nursery, their lives stretching across trillions of years. Their flames, though gentle, are eternal, a cosmic hearth that grants to the worlds orbiting them a boundless generosity of time. Any nascent flicker of biology that awakens in such a system might be granted eons beyond human comprehension to gestate, adapt, and transform. When the initial findings were disseminated, the scientific world paused, collectively holding its breath. For decades, the quest had been for Earth's celestial doppelganger, a rocky twin orbiting a yellow sun. Yet here was something entirely novel, and in its unique configuration, perhaps even more profoundly suited to the intricate dance of life. K2-18b was not a mere echo of Earth. It was an entirely new archetype of habitable world. Vast, hydrogen-rich oceans beneath alien skies, a biosphere sustained not by mimicry of our own conditions, but by the boundless, creative ingenuity of the universe itself. To perceive such a world, Webb had to orchestrate miracles of engineering and astrophysical prowess. Suspended 1 million miles from its origin point, at the gravitational sanctuary of L2, the telescope exists in an eternal twilight. Its 5-layered sun shield, an expanse the size of a tennis court, maintains an internal temperature colder than the frigid surface of Pluto. 18 golden mirrors, each a hexagon of perfected geometry, coalesce to capture light invisible to the human retina. Together, they forge a reflective surface so exquisitely precise it can discern the faint warmth radiated by a bumblebee navigating the lunar surface. When that distant planet, K2-18b, gracefully drifts across the face of its star, a minuscule fraction of starlight is filtered through its extensive atmosphere. Molecules suspended within that ethereal envelope absorb specific wavelengths of light, leaving behind faint ghostly imprints, a spectral fingerprint. By painstakingly decoding these intricate patterns, Webb unveils the planet's atmospheric chemistry. It is akin to discerning the unique timbre of a voice by the subtle modulation of its breath. Yet, to apprehend such a delicate whisper is an undertaking of almost unimaginable difficulty. The host star, in its incandescent glory, shines billions of times brighter than its planetary companion. To circumvent this overwhelming glare, Webb employs its coronagraph, an ingenious mask that eclipses the star's brilliance, much like shielding the sun with a thumb to discern the faint flicker of a firefly in the nearby darkness. The residual starlight, now bereft of its blinding intensity, is meticulously filtered, analysed, and purged of extraneous noise by algorithms so extraordinarily precise they can distill a mere handful of meaningful photons from a torrent of millions of empty ones. These precious photons, having embarked on their journey 120 years prior, roughly correlating to the epoch when humanity first began to broadcast radio waves into the heavens, carry stories older than human memory. Now, a century later, they reveal an astonishing truth. Life was already flourishing elsewhere, a testament to the universe's prolific creativity. It is a humbling realization to comprehend that we are not witnessing the nascent spark of life's genesis, but rather catching an echo of its established vitality, a century-old reverberation from a living world that has, in all probability, continued its enduring metabolic rhythms ever since. The planetary atmosphere, in its astonishing eloquence, revealed far more than mere chemistry. It offered a glimpse into behaviour, a planetary metabolism writ large. The intricate interplay of methane, carbon dioxide and water vapour formed a delicate dynamic equilibrium. On a world barren of life, such reactive gases would swiftly engage in chemical reactions, eventually settling into a sterile, predictable equilibrium. But equilibrium was not the narrative Webb observed. Instead, the ratios of these vital gases fluctuated, danced, and deviated from inert stasis, a chemical disequilibrium, the very signature that imbues Earth's living air with its vibrant breath. Life, in its ceaseless endeavour, does not permit static balance. It perpetually sculpts and reshapes its environment, inhaling, consuming, exhaling, a ceaseless feedback loop. Even the planetary atmosphere's missing gases articulated a profound story. Were K2-18b a lifeless entity, its skies would likely be saturated with ammonia. Yet, ammonia was almost entirely absent, as if some unseen agency were actively utilising it, transforming it, purifying the air. On Earth, legions of microbes perform precisely this vital function. The deeper the analytical probe delved, the clearer the emergent tableau became. Not a sterile, inert world, but a thriving, intricate biosphere. Not a mere fluke of random chemistry, but an ecosystem operating on a planetary scale. Statistically, the confidence achieved was overwhelming, a 3 sigma detection, implying a 99.7% certainty, a statistical robustness signifying a mere 1 in 1,000 chance of error. In almost any other scientific domain, such a finding would transcend all doubt, and yet no quantifiable number could adequately encompass the sheer epical enormity of its implications. For millennia, humanity had grappled with the profound query of whether life existed beyond our terrestrial cradle. Now, for the first time, the answer transcended mere speculation. It manifested as empirical measurement. To arrive at this conclusion, Webb had to discern molecular patterns of an almost infinitesimal strength, a few parts per billion, the spectral equivalent of perceiving a faint heartbeat amidst the cacophony of a hurricane. Light itself was measured to 1 part in 10 million, each wavelength meticulously recorded and comparatively analysed, every conceivable alternative explanation systematically and rigorously ruled out. Contamination originating from Earth was deemed an impossibility. Random noise, statistically negligible. The most parsimonious explanation, indeed the only coherent explanation, was biology. This profound understanding explains why, in the moment the data was corroborated, every scientist who witnessed it felt the same quiet, resonant weight settle upon their consciousness. This was not merely another exoplanet, it was, in its deepest essence, the termination of cosmic solitude. The planet's immense oceans, speculated to plunge for hundreds of miles, blur the very distinction between the aqueous deep and the atmospheric vault. Within these abyssal reaches, water merges with hydrogen, forging a liquid unlike any found on Earth, a unique solvent that maintains its fluid integrity across a staggering spectrum of temperatures and pressures. Such exotic chemistry holds the potential to nurture life forms beyond the wildest human imagination. Creatures that might respire hydrogen instead of oxygen, deriving their metabolic sustenance from methane rather than the familiar embrace of sunlight. Beneath its perpetual shroud of clouds, atmospheric pressure accumulates, generating conditions that we can scarcely replicate within our most advanced terrestrial laboratories. Diamonds, perhaps, may crystallize and descend as glittering rain, showering through the atmosphere into the vast, warm oceans below, like frozen stars returning to their watery birthright. Somewhere beneath that luminous haze, within the perpetually warm twilit waters, life is almost certainly stirring, not fragile, not ephemeral, but ancient, robust, and abundant. This realization, in its cosmic sweep, fundamentally alters our perspective. If biology can not only survive but thrive within hydrogen-rich seas orbiting a red dwarf star, then the emergence of life is not an improbable rarity. It is an intrinsic inevitability. 3/4 of the stars that illuminate our galaxy are red dwarfs, quiet, enduring suns, many of them cradling planets strikingly similar to K2-18b. If even a fraction of these worlds host nascent biospheres, then our Milky Way galaxy, far from a silent expanse, must be teeming, overflowing with living worlds. This discovery irrevocably redefines the very lexicon of habitable. It instructs us that life does not necessitate an exact clone of Earth. It demands only balance, the precise chemistry, the optimal temperature, and above all the cosmic virtue of patience. Webb's golden mirrors transcended mere observation. They forged a connection, linking us to another profound chapter in the grand narrative of creation. Each photon it ensnared carried a faint whisper across the immense gulf of space and time, the spectral breath of an unseen ocean, the silent sigh of life beyond our immediate grasp. In that faint luminous message, humanity found irrefutable proof that existence is shared, that we are neither the first nor the only, and most assuredly not the last. The universe, it seems, has been vibrantly alive for durations that defy our logical imagination. The red dwarf star at the heart of the K2-18 system, though small enough to be engulfed by Jupiter, possesses sufficient density to anchor a world like K2-18b within its gravitational embrace for eons stretching into eternity. Its light, a deep, resonant ember red, rather than the fierce white blaze of our sun, would to human eyes not incinerate but gently glow, soft, unwavering, patient. This is not a star destined for a brief, incandescent life, but one that burns slowly, almost tenderly, its lifespan extending not into billions but into trillions of years. On the immeasurable timescale of the cosmos, it is virtually immortal. That profound longevity is a game-changer. Around our sun, light fluctuates. Climates oscillate wildly, and epochs of mass extinction have sculpted the brutal narrative of evolution. But around this quiet, patient star, the light remains an unwavering constant. The same warmth, century after century, millennium after millennium. No cataclysmic flares to strip away a fragile atmosphere. No gravitational chaos to undo the intricate work of biochemistry. For a world like K2-18b, this stellar constancy translates into something extraordinary. Oceans that never surrender to ice, clouds that never dissipate into the void, and time, an almost infinite expanse of time, for life to awaken, adapt, and endure. For decades, scientific consensus largely dismissed red dwarfs as unsuitable nurseries for life. They are small, relatively cool, and their habitable zones cling so intimately to the star that any orbiting planet must almost embrace its fiery parent. But what was once perceived as perilous now reveals itself as potentially ideal. K2-18b completes its orbital year in a mere 33 Earth days, close enough to bask in the gentle warmth of its dim sun, yet sufficiently distant to maintain atmospheric stability. One hemisphere perpetually bathes in the crimson glow of its daylight, while the other slumbers in eternal darkness. From the vantage point of space, it would appear as a glowing marble, half immersed in a perpetual twilight of crimson, half shrouded in shadow. Yet even that night side is spared the icy grip of absolute cold. The planet's colossal hydrogen atmosphere acts as a vast, efficient conveyor belt of heat. meticulously distributing thermal energy across its entire celestial sphere. This atmospheric stability, a rare gift in the tumultuous universe, bestows permanence upon its water, allows meteorological phenomena to unfold without catastrophic violence, and grants the intricate dance of chemistry a profound tranquility. If life indeed exists there, it would have evolved beneath a sun that never truly rises nor ever truly sets, a world suspended between an eternal dawn and an unending dusk, where the boundary delineating day from night is not a stark frontier, but a sprawling habitable biome. Under that perpetual twilight, the sky would forsake the familiar azure of Earth. Instead, it would burn in layered hues of crimson, violet, and copper, dim, certainly, but ceaseless. The red dwarf star would hang motionless above the horizon, forever fixed in its singular celestial station. The oceans below would mirror that sanguine light, glowing faintly as slow, viscous waves moved beneath a horizon blurred by atmospheric haze. On the night side, darkness would not be absolute. The dense, scattering air would diffuse the faint starlight, painting the inky blackness in subtle metallic hues. Even there, a residual light would linger, the ephemeral shimmer of auroras, the distant flash of lightning within remote cloud formations. This is not a planet of stark contrasts, but of gradual, elegant gradients, where every transition unfolds smoothly, never abruptly. If evolution unfurled its delicate wings here, it did so with an unparalleled patience. On Earth, life was brutally forged by disaster, asteroid impacts, glacial epochs, sudden, fiery cataclysms. But around this quiet, unwavering sun, the concept of mass extinctions, of abrupt biological endings, is perhaps alien. The rhythm of cosmic time is slower, the canvas of existence infinitely broader. Life here could mature through untold eons without interruption, carried forward on the calm, measured breath of a red dwarf dawn. Webb's instruments were exquisitely designed to perceive in this precise wavelength of light. Infrared, the very spectrum red dwarfs emit most strongly. This intrinsic alignment rendered K2-18b's atmospheric signature exceptionally clear. The telescope was not straining to glimpse a faint, elusive presence. It was harmonically tuned to the intrinsic language of the star itself. Every beam of infrared light carried within it the encrypted code of the planet's atmosphere, the subtle warmth of its hydrogen clouds, the pervasive scent of its deep oceans, the very breath of unseen organisms. Each time the planet gracefully crossed the face of its star, a minuscule fraction of starlight traversed its atmospheric layers. Molecules within that atmosphere absorbed specific wavelengths of this light, leaving behind faint distinctive notches, spectral fingerprints. Webb meticulously deciphered them like an ancient diary meticulously transcribed in light. The pages spoke of water, of methane, of carbon dioxide, and then, most profoundly, of dimethyl sulfide, the indelible mark of life itself. To the naked human eye, the red dwarf would appear utterly unremarkable, barely discernible in the terrestrial night sky. Yet that very dimness, counterintuitively, is what enables such profound discovery. The smaller and cooler the star, the less overwhelming its glare, rendering its orbiting planets more readily observable. The signals emanating from them are cleaner, less obscured. What appears weak is, in truth, perfectly calibrated for revelation. Red dwarfs are not celestial impediments. They are in essence cosmic magnifying glasses, meticulously revealing the faint, vital whispers of their hidden worlds. If we could, by some impossible grace, stand upon one of K2-18b's elevated plateaus and gaze upwards, the vista would transcend surrealism. The horizon would curve beneath a bronze sky, the air shimmering with a pervasive internal warmth. The sunlight, diffused and mellow, would feel less like incandescent brightness and more like a tender enveloping heat. Shadows would stretch long and languid, extending into an apparent eternity. The familiar terrestrial dichotomy of day and night would dissolve, replaced by slow, imperceptible shifts in atmospheric tone, in temperature, in the very measured heartbeat of the planet itself. Life, should it indeed exist there, would move to a different cadence. Photosynthetic organisms might manifest in deep, sombre hues, black, indigo, or profound violet, meticulously absorbing every stray photon of red light. Their metabolic processes would be slow yet unswervingly steady. The creatures that grazed upon them might perceive their world through vibrations, through subtle pressure gradients, rather than through the primacy of sight. Nothing would be hurried. Energy, though diffused, is constant, and time in this realm is an infinite endowment. Evolution would reward a profound patience over frenetic speed, enduring resilience over aggressive competition. The red dwarf's most profound gift is moderation. It burns with an almost ascetic discipline, never wasteful, never surging in destructive flares, while our sun, in its majestic but finite span, will expand and eventually expire within the next 5 billion years. K2-18's parent star will still be softly glowing when the Milky Way galaxy is transmuted beyond human recognition. For the life orbiting it, the concept of apocalypse is a word utterly devoid of meaning. When Webb-sensitive instruments detected light originating from K2-18b, that light had already been traversing the cosmic void for 120 years. When it embarked on its epic journey, the year on Earth was 1905. Einstein was meticulously formulating his revolutionary theories of relativity. The Wright brothers were still refining their nascent experiments in sustained flight. Our species, in its early infancy, had barely begun to comprehend the mechanics of reaching the sky, while that distant planet had already been breathing beneath a complex atmosphere for untold eons. This profound temporal disparity means that what we perceive is not the present actuality, but a profound echo of the past, a memory of a living world as it existed a century ago. And when we redirect our gaze decades hence, we will still be perpetually catching up to that specific temporal moment. Astronomy, in its deepest essence, is always a conversation across the vast, intricate tapestry of time, and the universe in its majestic deliberations speaks with an unhurried slowness. Yet, even a faint whisper from 120 light-years away possesses the potency to rewrite the very foundations of our belief. The intricate chemistry detected within that alien air, the unique melange of gases, the profound disequilibrium that only the ceaseless metabolic activity of life can sustain, dances to the steady rhythmic beat of its patient star. The red dwarf bestows an unyielding constancy. The planet, in response, expresses a vibrant metabolism. Together they forge a perfect self-sustaining loop, one immutable, the other exquisitely alive. It is a relationship forged of cosmic opposites, a duet between the primordial fire of a star and the gentle breath of a living world. The star imparts stability, the planet, perpetual change. One consumes, the other perpetually renews. Our own world began in tumultuous chaos, fire, cataclysmic impacts, the raw unbridled violence of a nascent solar system. But around a quiet, enduring red dwarf, life could have embarked upon its journey in profound peace. The stellar glow is faint, yes, but for a world like K2-18b, it is gloriously sufficient. Enough warmth to cradle vast oceans, enough light to catalyse intricate chemistry, enough time for everything. Perhaps this is the universe's quiet, profound truth, that life does not necessarily crave incandescent brilliance, but rather a profound, enduring balance, that it can unfurl its delicate bloom under crimson skies as effortlessly as beneath our familiar blue. That existence itself is fundamentally adaptable, universal, and imbued with an immense cosmic patience. Thus, when we direct our gaze towards the constellation of Leo and perceive that faint, ruddy spark, we are not witnessing an expanse of emptiness. We are witnessing endurance, a sun that has burned softly for billions of years and is destined to burn for trillions more. And beneath its calm, unwavering glow, behind curtains of hydrogen and mist, a living world may still be turning slowly, silently, in the patient light of an immortal star. The light emanating from K2-18b's red sun embarks on its journey through layers of hydrogen and vapour before finally descending into the vast hidden oceans below. To the human eye, those alien skies would not register as blue, but rather as a pale, shimmering amber, gradually deepening to a profound rose near the curvilinear horizon. Clouds would drift with an unhurried grace, broad and immensely dense, subtly tinted by the faint coppery glow of the steadfast star. The very air itself would shimmer, heavy, rich, almost luminous, a living lens of gas that simultaneously shields and sustains the enigmatic realm that lies beneath. This colossal atmosphere is the planet's grand, silent architect. It is not thin and fragile like Earth's delicate envelope, but vast and immensely thick, plunging for hundreds of kilometres. Hydrogen dominates its composition, intricately laced with carbon dioxide, methane, and abundant water vapour. Together these elements conspire to create a formidable greenhouse effect, yet one that is, remarkably, not destructive. Instead of scorching the surface into an inferno, the trapped heat diffuses evenly, meticulously maintaining the entire world in a state of profound thermal equilibrium. Water neither succumbs to freezing nor yields to boiling, it simply endures, flowing through endless self-regulating cycles of vapour and precipitation. From an orbital vantage point, the upper atmospheric layers present an aspect of serene tranquility. However, as one descends deeper, the air grows progressively dense to a point where the very distinction between sky and sea begins to blur, then dissolve. Clouds merge seamlessly with mist. Mist, in turn, subtly dissipates into the boundless ocean. The boundary separating air from water is not a distinct surface, but rather an elegant gradient, a slow, continuous fading of one essential element into the other. Beneath that soft, enveloping veil, the crimson sunlight gradually weakens, eventually replaced by an internal sanguine glow that permeates the depths like light filtering through ancient stained glass. The ocean itself may stretch for hundreds of kilometres in depth, plunging far beyond any pressure our most advanced submersibles could possibly withstand. Hydrogen, in an extraordinary aquatic alchemy, mixes freely with the water, creating a liquid unlike any found on Earth, lighter, significantly more compressible, and crucially capable of maintaining its fluid state across an enormous range of temperatures and pressures. It is a sea where the intricate dance of chemistry reigns supreme, a primordial cradle of molecules poised to assemble, divide, and breathe in entirely novel ways. If life indeed exists there, it most likely originated within those profound depths, far from the direct reach of any stellar light. On Earth, for a long time, we erroneously believed that sunlight was an indispensable prerequisite for the very act of creation. Yet, at the bottom of our own abyssal oceans, clustered around searing hydrothermal vents, we discovered entire ecosystems that flourish in absolute darkness, powered not by the sun's radiant energy, but by the raw, untamed forces of chemistry. They subsist on heat and dissolved minerals, exploiting gradients of energy rather than photons from above. The same profound truth could very well apply to K2-18b. Its deep oceans may harbour extensive hydrothermal fields, where hydrogen and carbon atoms mingle in a ceaseless reactive ballet, potentially giving rise to the very first spark of biology. The pressures in those unfathomable depths would effortlessly crush steel. Yet, for living cells, Such extreme pressure can paradoxically act as a form of protection. It stabilizes fragile biomolecules, drives complex chemical reactions forward, and critically maintains water in its liquid phase, even when temperatures soar to otherwise boiling points. If microbial life ever took hold in those primordial depths, evolution would have been granted billions of calm, uninterrupted years to hone and perfect them. Webb's sophisticated instruments, by their very nature, cannot penetrate that far below the obscuring cloud layers. However, the atmosphere above, in its eloquent chemistry, betrays the vibrant processes unfolding beneath. The gases we detect, methane, carbon dioxide, and the telltale traces of dimethyl sulfide, strongly suggest an active, dynamic cycle connecting the immense sea with the overlying sky. On Earth, this delicate planetary balance is meticulously maintained by the ubiquitous presence of life itself, algae producing methane, specific microbes consuming it, plants exhaling oxygen. On K2-18b, a strikingly similar dynamic could be at play, albeit one shaped by profoundly different biochemical rules. The conspicuous absence of ammonia serves as yet another compelling clue. On geologically dead planets, ammonia tends to accumulate over vast timescales, a passive byproduct of chemical decomposition. But here, it is conspicuously missing, most likely converted into more complex organic compounds or actively broken apart by ongoing living metabolism. Even without directly observing a single organism, the atmosphere behaves as if it is being constantly adjusted, meticulously tuned, and perpetually renewed by an unseen, living hand. Imagine, for a moment, standing, or perhaps more accurately floating, somewhere within that dense alien environment. The air would possess a palpable viscosity, dense enough to feel like an enveloping liquid around you. Sound would propagate slowly but with a profound clarity, vibrations passing through the fluid medium in deep, resonant waves. A single droplet of the ocean within which you might be suspended would contain more sheer pressure than the deepest point of Earth's Mariana Trench. Yet to any native life forms, such conditions would feel entirely natural, perfectly balanced, and serenely conducive to existence. Light would diminish rapidly with increasing depth. Just a few hundred meters down, the world would transition into a realm of red-black, illuminated solely by faint, sporadic chemical luminescence, life's own adaptive answer to the pervasive darkness. Perhaps tiny bioluminescent organisms drift there, glowing softly, exchanging heat and light as a form of intricate communication. Perhaps immense, slow-moving creatures glide through the warm, abyssal currents, perceiving one another through subtle electric fields and complex pressure waves. Every metabolic breath of that ocean would be a chemical reaction in constant, vibrant motion. Methane, perpetually rising from the depths, would mingle with carbon dioxide descending from above, giving rise to novel compounds that nourish microscopic life. Hydrogen, dissolved ubiquitously within the water, would serve as both protective shield and vital fuel source. On Earth, such fundamental chemistry painstakingly builds the intricate architecture of cells. Here, it might be constructing something far stranger, far more alien, a biology that functions without any reliance on oxygen whatsoever, and yet, in many profound ways, it would still feel strangely familiar. Wherever we encounter life, we invariably discover balance. Energy flows in intricate cycles, waste is perpetually repurposed as sustenance, and stability is maintained through the very act of constant dynamic change. That, precisely, is what Webb has so eloquently observed in the precise ratios of gases high above K2-18b's clouds, a living system meticulously regulating itself. In the mid-layers of K2-18b's expansive atmosphere, temperatures and pressures remarkably converge with those found near Earth's surface. If any part of this world could potentially host organisms analogous to our own, it would be within this aerial stratum, suspended like ethereal plankton in an invisible, planetary ocean of gas. Tiny, resilient microbial colonies might drift effortlessly with the atmospheric currents, metabolically feeding on trace chemicals, gently absorbing the diffuse red light from their distant sun. Each such colony would represent a mere speck of life, perpetually carried by the planetary winds, gracefully rising and falling through a planet-wide ocean of breathable air. We already possess tantalizing hints that such aerial worlds could exist. In the incredibly dense sulfuric clouds of Venus, scientists have detected patterns of chemistry that strongly suggest the presence of floating microbes high above the scorching surface. K2-18b's atmosphere, by stark contrast, is immeasurably gentler, devoid of corrosive acid storms, free from suffocating runaway heat, rendering it an even more compelling candidate for harbouring aerial life. If the unfathomable oceans below represent the planet's profound heart, then its vast atmosphere is undeniably its very breath. Every molecule of methane or dimethyl sulfide that escapes the deep sea becomes a silent message, drifting upwards into the starlight. Those very molecules, after traversing unimaginable distances, touched Webb's golden mirrors, carrying with them the unmistakable rhythm of metabolism, the subtle, enduring pulse of an alien biosphere. The profound beauty of this monumental discovery lies in our capacity to decipher that message without ever needing to physically depart our home world. We can remain anchored on our quiet planet, orbiting our own familiar star, and solely through the medium of light, meticulously reconstruct another world's climate, its intricate chemistry, and perhaps its very biology. From the tiniest, almost imperceptible distortions in a beam of infrared light, we can now discern whether another distant ocean ripples, whether another alien sky holds the promise of rain. And rain it most assuredly does. Water vapour within K2-18b's atmosphere coalesces into massive swirling clouds that rise and fall in slow, majestic convection cycles. As these colossal formations cool, they release precipitation that descends not as discrete drops, but as ethereal sheets, thick as mist, gliding gracefully through the dense air until they finally vanish into the even deeper, more pressurized layers below. There, the immense pressure is so profound that the descending rain may undergo a phase transition, turning into liquid metal or crystalline ice before ultimately sinking into the hydrogen-rich ocean below. Every conceivable state of water, vapour, liquid, and solid could potentially coexist simultaneously, meticulously stacked in layers like the unfolding pages of a grand cosmic narrative. That fundamental hydrological cycle, evaporation, condensation, rainfall, is the very same elemental process that sculpted Earth's weather patterns and assiduously nourished its life. It serves as a poignant reminder that even across the vast gulfs of light years, the intrinsic language of nature is universal. Chemistry, in its elegant precision, adheres to the same grammatical rules everywhere in the cosmos. The deeper scientists peer into this distant world, the clearer it becomes that K2-18b is not merely habitable in abstract theory, but vibrantly dynamic in tangible practice. The planet breathes, it recycles, it constantly changes. Each new observation invariably reveals motion, intricate feedback loops, and profound adaptation, the undeniable hallmarks of a living system operating on a planetary scale. Somewhere beneath those perpetual clouds, in the pressurized warmth of those alien, hydrogen-infused seas, evolution may have already sculpted life into astonishingly diverse and complex forms. Simple, rudimentary cells could have merged into cooperative colonies. These colonies, in turn, could have developed the capacity to sense, to move, to think, all at a pace measured not in fleeting millions of years, but in the majestic sweep of billions. The red dwarf's slow, unwavering heartbeat grants evolution the ultimate luxury, uninterrupted time to unfurl its intricate tapestry. We will likely never perceive these distant life forms directly, not yet. But the air they exhale, the molecules they purposefully release, have already traversed the immense void to reach us. These are tiny, eloquent signatures of existence, carried across the vast expanse of space. They serve as irrefutable proof that we are no longer merely passive observers of the cosmos, but active participants in its oldest, most profound conversation, the timeless reciprocal exchange between light and life. As the James Webb Space Telescope continues its unwavering gaze upon this extraordinary world, every single photon it meticulously captures brings us incrementally closer to comprehending the unseen. The next crucial step in this cosmic investigation will involve mapping the intricate layers of that alien atmosphere in even finer, more granular detail, to precisely measure how the light shifts, how the powerful winds move, how the complex chemistry itself evolves from one year to the next. For now, however, it is enough to grasp this profound truth. Somewhere beneath a crimson sun, beneath clouds that shimmer with the delicate iridescence of silk, and above oceans that seemingly never end, there exists a profound balance. A living, breathing equilibrium between pervasive heat and ambient cold, between a dense, living air and an unfathomable sea, between the patient light of a star and the vibrant pulse of a planet. It is a balance so exquisitely perfect, it almost evokes a sense of intentionality, not by conscious design, perhaps, but as an inherent, inevitable consequence of the universe's fundamental laws, as though the cosmos itself relentlessly seeks to manifest life wherever the conditions permit, and on K2-Soraiten-b it may have found one of its most enduring, most tenacious homes, a world breathing softly in the eternal light of a red star, a world whose profound oceans perhaps remember the very first warmth of creation, and whose sky carries the quiet, steady pulse of an enduring alien life. For centuries humanity cast its gaze upon the stars, perceiving only an expanse of profound silence. Then came K2-Soraiten-b, not the anticipated twin of Earth, a reflection of our own genesis, but something far more mysterious and ultimately more expansive, an ocean world, eternally shrouded in hydrogen, faithfully orbiting a red sun light years distant from anything we had ever dared to call home. Its discovery did not merely broaden the scope of astronomy, it fundamentally expanded the very horizons of imagination itself. For the first time in recorded history, we are not simply contemplating the theoretical possibility of life elsewhere. We are witnessing the tangible spectroscopic signs that it exists. When Webb's golden mirrors unveiled the faint, eloquent traces of dimethyl sulfide, it was more than just a data point. It was a seismic tremor resonating through the human narrative. In a few delicate lines of a spectrum, the perceived silence of the universe cracked open, not with an audible sound, but with irrefutable evidence. That singular, tenacious molecule bridged an immense chasm between worlds. It stated softly yet unmistakably, "You are not alone." The profound meaning of that statement transcends mere percentages or statistical confidence levels. It reaches far deeper than the empirical realm of science, burrowing into the intricate tapestries of philosophy, art, belief, and the very core of human identity. It compels us to re-envision life not as an improbable exception, but as a fundamental, pervasive principle woven into the fabric of existence. For generations, we harboured the conviction that life was a cosmic rarity, that biology was an improbable accident born solely from a unique convergence of perfect conditions on Earth. Yet, our blue planet has never been the sole stage upon which the universal laws of chemistry orchestrate their intricate play. These laws have been performing their grand cosmic opera across the galaxy for billions of years, tirelessly seeking the precise balance between raw energy and emergent order. We have already glimpsed these tantalizing hints. resilient microbes thriving in the hostile glow of nuclear waste, bacteria slumbering for millennia beneath the crushing weight of Antarctic ice, and bizarre creatures flourishing kilometers beneath our own oceans, drawing sustenance not from sunlight, but from the geothermal heat of the Earth itself. Life, it appears, does not passively await comfort. It tenaciously thrives in defiant contradiction of it. And now, 120 light-years away, a world breathes under a red sun, offering compelling proof that existence, far from being fragile, is imbued with an inherent, unwavering persistence. If K2-18b indeed hosts life, it fundamentally reshapes everything we thought we knew, because red dwarfs, like its patient parent star, are overwhelmingly the most common stellar bodies in the Milky Way. For every star analogous to our Sun, there are literally thousands of these smaller, older, and significantly steadier celestial hearths. If even a minuscule fraction of these countless red dwarfs harbour planets akin to K2-18b, then the galaxy, far from being a silent, empty expanse, is a teeming, vibrant tapestry of life. Billions of worlds, billions of nascent beginnings. The implications of this reach far beyond the confines of astronomy, extending deep into the very equations that attempt to quantify our cosmic solitude. The Drake equation, for decades a speculative thought experiment, a fragile human endeavour to estimate the number of intelligent civilizations, now sees one of its most uncertain variables, the likelihood of life emerging, shift from a monumental question mark to an almost irrefutable near certainty. Life, it seems, does not patiently await Earth-like conditions. It emerges wherever chemistry and the boundless expanse of time are afforded the opportunity to coalesce and unfold. If biology can indeed respire hydrogen, if oceans can thrive beneath the gentle, enduring light of red suns, then the very definition of habitable becomes almost universally inclusive. It irrevocably changes how we perceive ourselves within the cosmic order. For the vast majority of human history, our narratives invariably placed humanity at the absolute centre, chosen, unique, divinely appointed, surrounded by an encompassing divine emptiness. Then came Copernicus, who, with a single stroke of genius, moved Earth from the sacred centre of creation. Then Darwin, who humbly situated humanity within the grand tapestry of nature rather than arrogantly above it. And now Webb, which has elevated life itself from the realm of inexplicable miracle to an inherent rhythmic expression of fundamental physics. We are not an isolated exception. We are an eloquent expression, one single verse in a cosmic song that began eons before us and will resonate long after our species has faded into stardust. And yet, this profound realization does not diminish us in the slightest. It profoundly connects us. It signifies that the very atoms composing our bodies, forged in the fiery crucible of dying stars, may also breathe and cogitate elsewhere in the cosmos. The same fundamental chemistry that pulses through our terrestrial blood may flow through vast alien oceans. The identical physics that ignited our sun fuels 1 trillion others across the boundless firmament. The James Webb Space Telescope has, in essence, become a new human sense organ. Not merely eyes or ears, but something far deeper, a profound capacity to perceive life through the subtle language of light. Each photon it meticulously captures is a vital syllable in the grand, unfolding language of existence, travelling for over a century to finally reach our eager senses. And Webb is not alone in its monumental quest. Other sophisticated observatories, the upcoming Nancy Grace Roman Space Telescope, the conceptual Ariel and Louvois missions, and future ground-based giants, are already under construction, designed to continue this relentless cosmic hunt. Soon, we will possess the unprecedented capability to analyse not just one distant world, but hundreds. If even a handful of these revelations exhibit the same tantalising chemical imbalance, the same quiet whispers of metabolism, then life is not an isolated miracle. It is a recurring, fundamental pattern woven throughout the cosmos. Imagine the profound night when we collectively realize that every constellation in the heavens secretly conceals a living world, each faint glittering star a sun, cradling its own oceans, its own dynamic clouds, and its own intricate living chemistry. Some of those worlds may be primordial, existing in a nascent biological state. Others could be ancient beyond human comprehension, their civilizations having ascended to dizzying heights and then quietly dissolved into the cosmic dust long before the first humans ever carved a symbol into stone. But even if we never achieve direct contact, their mere existence fundamentally transmutes the meaning of our own, because for the first time, we possess empirical knowledge that life on other worlds is far more accessible and ubiquitous than we ever dared to imagine. For both philosophy and faith alike, this groundbreaking discovery fundamentally reframes everything. If life, in its myriad forms, truly saturates the galaxy, then the act of creation itself is not selective. It is boundless, an overflowing abundance. The concept of the sacred becomes not something that transpired once in a solitary location, but something that perpetually manifests wherever matter organizes itself into vibrant complexity. The true miracle is not that life exists here on Earth, but that the universe, in its inherent generosity, allows it to flourish everywhere. And yet, this profound revelation carries within it a sobering mirror. We have found compelling proof that life may valiantly thrive under the most alien of skies, while our own fragile existence, under the nurturing warmth of a bright yellow sun, trembles under the increasing weight of our own terrestrial making. K2 Sund 18b, in its cosmic serenity, appears balanced, steady, enduring. Earth, by poignant comparison, feels increasingly restless and fragile. The universe, through K2 18b, has eloquently shown us what true planetary sustainability looks like, not as an elusive political ideal, but as a fundamental immutable natural law. Perhaps this is the most profound lesson K2 18b imparts, that ultimate survival is not predicated upon domination, but upon achieving a harmonious equilibrium. Life endures longest, not when it conquers and subjugates, but when it cooperates, when it orchestrates a delicate, ceaseless dance of interdependence. When the historians of a distant future inevitably cast their gaze backward, they may well designate this as the pivotal moment when astronomy seamlessly transitioned into biology, when we ceased merely studying the properties of light and commenced the far more profound endeavour of studying life itself through its luminous emanations. Webb's golden mirrors, silently suspended in the cosmic void a million miles away, have become more than mere scientific instruments. They are shimmering bridges linking our small blue world to something immeasurably vast and enduring. Because even now, as Webb diligently listens, our own signals are inexorably propagating outward. Radio waves, antiquated television broadcasts, the ceaseless digital heartbeat of our terrestrial civilization, they are expanding through the silent expanse of space at the immutable speed of light. They are crossing the immense distance to K2 18b and far, far beyond. Somewhere, if that distant world truly breathes with life, our faint ethereal signals may have already arrived, and perhaps, on its crimson shores, something alive has momentarily paused, sensing a faint rhythmic pattern, a subtle cadence within the pervasive static, a nascent sign that it too is not utterly alone. If that momentous conjunction ever transpires, if two worlds, separated by an astounding 120 light-years, mutually recognize each other's profound presence, it might well constitute the greatest conversation in the entire annals of history. Not through the clumsy constructs of language, not through the ephemeral vibrations of sound, but through the eternal, universal medium of light itself. Until that distant epoch, what Webb has already revealed to us is profoundly sufficient. sufficient to know that the universe is not the empty, silent void we once imagined, but is instead resonating with hidden, intricate songs, sufficient to understand that life is not a fragile anomaly, but an inherent, almost inevitable expression of cosmic processes, sufficient to humbly remind us that every molecule of air we inhale, every single drop of ocean that laps our shores, every single breath we draw, intrinsically connects us to something immeasurably older and infinitely greater than our individual selves. And as Webb continues its unwavering gaze into the profound darkness, meticulously collecting the faintest, most ancient whispers of alien seas and skies, we begin, finally, to comprehend the truth that has patiently awaited our hearing for so long. The cosmos is profoundly, vibrantly alive. The discovery on K2-18b is not an ending. It is, in its deepest essence, a new beginning. It is the first empirically measured hint that life, in its myriad manifestations, may not be confined solely to our terrestrial cradle. From this pivotal moment forward, the very nature of our cosmic inquiry irrevocably changes. We no longer timidly ask if life exists elsewhere, but rather how many diverse forms it might gracefully assume, and how far its vibrant tendrils might extend across the galactic tapestry. Science itself is undergoing a profound paradigm shift. For the very first time, the hitherto distinct disciplines of astronomy, chemistry, and biology are seamlessly merging into one overarching discipline, a unified search for the fundamental patterns that define and enable life across the boundless expanse of the galaxy. Researchers are now terming this burgeoning field comparative astrobiology, the holistic study of atmospheres, climates, and intricate chemistries as an interconnected living system. No longer isolated dots of light, distant planets are transforming into vital data points in a dynamic, living map of the cosmos. On Earth, new cutting-edge laboratories are meticulously recreating the extreme conditions found on alien worlds. Pressurized chambers ingeniously mimic the dense, hydrogen-rich skies of sub-Neptune planets, meticulously testing how fundamental elements like carbon, nitrogen, and water behave under temperatures and pressures utterly alien to our terrestrial experience. Some of these ambitious experiments run for many months, patiently observing molecules as they gradually evolve into complex organic compounds, the very precursors that may one day illuminate the initial spark of biology anywhere in the universe. Other research endeavours focus intently on the chemistry of equilibrium, relentlessly searching for that elusive, magical point where pure, inert physics gives way to the dynamic, self-sustaining processes of metabolism. The ultimate goal is to construct a comprehensive library of biosignatures, an exhaustive catalogue of what genuinely living atmospheres truly appear like, regardless of their specific chemical composition. Artificial intelligence is quietly, yet profoundly, becoming the indispensable interpreter of this new era of astronomy. Sophisticated machine learning systems, meticulously trained on Webb's vast and intricate datasets, are now capable of recognizing molecular patterns utterly invisible to the limitations of the human eye. Faint, subtle combinations of gases,
not
minute seasonal fluctuations,
kinship.
Tiny, almost imperceptible variations in brightness that might eloquently indicate alien weather systems or gradual biological growth. What once demanded months of painstaking manual analysis by human scientists now transpires in mere minutes. Each new data set meticulously refines these algorithms further, iteratively teaching machines to detect the smallest, most elusive chemical heartbeat within the vast, overwhelming noise of interstellar space. Around Earth, a new generation of telescopes is currently preparing to embark upon the next series of monumental leaps. The Nancy Grace Roman Space Telescope, slated for launch later this decade, will embark on a mission to identify thousands of new exoplanets, providing the first truly large-scale census of their diverse types and orbital configurations. Europe's ambitious aerial mission will follow, dedicated to studying the atmospheres of 1,000 of these exoplanets in unprecedented detail. On the ground, the colossal, extremely large telescope in Chile, with its combination of adaptive optics and massive primary mirrors, will possess the power to measure the isotopic makeup of distant alien skies, subtle ratios that can provide invaluable clues as to whether a planet's atmospheric gases originate from purely geological processes or from the unmistakable presence of biology. Collectively, these observatories will form an intricately interlinked network, a planetary survey system of unparalleled scope, transforming distant, shimmering points of light into measurable, comparable, and increasingly understood worlds. The next truly epical leap will not solely reside in the sheer volume of data, but in the profound expansion of our observational vision. Engineers are tirelessly developing revolutionary new optical technologies, advanced coronagraphs and massive, deployable star shades, capable of blocking a star's blinding light so completely that the faint reflected glint of its orbiting planet becomes directly visible. A mere single pixel of that precious light can potentially reveal its colour, the extent of its cloud cover, and its rotational period. With a sufficient number of pixels, we might one day possess the astonishing ability to discern alien continents or vast oceans glinting under an unfamiliar sun. Ambitious concepts like NASA's Habitable Exoplanet Observatory, HabEx, and large ultraviolet optical infrared surveyor, LUVOIR missions, could render such direct imaging a tangible reality within mere decades. These monumental telescopes would not only detect the intricate chemistry of life, but would also observe its climate in dynamic motion, witnessing alien seasons, colossal storms, and the slow, inexorable rhythm of extraterrestrial weather patterns. Farther still into the distant future, another, even grander vision begins to take ethereal shape, utilizing the Sun itself as a colossal telescope. At a gravitational focal point located more than 550 times farther from our Sun than Earth's orbit, the Sun's immense gravity bends light from distant stars into a natural, powerful focus, creating what physicists term the solar gravitational lens. A small, advanced probe, meticulously dispatched to this distant point, could leverage this effect to magnify a distant planet by a staggering billion times, resolving details as fine as mountain ranges on its surface. While reaching such an immense distance would undeniably require many decades, the fundamental technology remains within the aspirational reach of 21st century engineering. While telescopes tirelessly study from afar, propulsion research looks steadfastly ahead to the ultimate frontier, not merely perceiving other worlds, but ultimately reaching them. Bold concepts like breakthrough starshot propose ambitious fleets of laser-driven nanocraft, propelled to a fifth the speed of light. Their initial targets will be nearby stellar neighbours such as Alpha Centauri. But the same revolutionary methods could eventually enable the dispatch of microprobes to worlds as distant and intriguing as K2-18b. Closer to our solar system's heart, new generations of propulsion systems, fusion drives, advanced ion engines, solar sails, are being meticulously developed and rigorously tested in missions across our own cosmic neighbourhood. Each innovative experiment in deep space navigation, each meticulous test of autonomous control, brings the seemingly futuristic technology of interstellar flight incrementally closer to tangible reality. Yet, the ultimate future of this profound discovery is not solely defined by the conquest of astronomical distance. It is equally, if not more, about deciphering its deep, transformative meaning. As an increasing number of exoplanets unveil tantalizing traces of chemistry that powerfully suggest the presence of life, scientists will transition from studying isolated examples to analyzing the overarching statistics of existence itself. What precise conditions does life intrinsically prefer? Red stars or yellow ones? Deep, abyssal oceans or shallow sunlit seas, profound isolation or intricate emergent complexity. By the middle of this century, the systematic study of life beyond Earth may no longer be a matter of rare, serendipitous finds, but rather a sophisticated discipline of pattern recognition, biology observed and understood on a truly galactic scale. This profound knowledge will not remain confined solely to the esoteric realm of astronomy. The very same sophisticated models employed to comprehend the atmospheric balance of other worlds can provide invaluable insights to help us preserve our own. Studying atmospheric equilibrium elsewhere sharpens our understanding of critical climate feedback loops here on Earth, how specific gases stabilize temperature, how vast oceans regulate heat, and how inherently fragile planetary equilibrium can truly be. In learning how other planets manage to sustain life, we may, ironically, learn how to keep our own world vibrantly alive. The implications of this discovery extend further still. If we definitively confirm the existence of life beyond Earth, even simple microbial life, it will irrevocably redefine the entire ethical landscape of space exploration. The Outer Space Treaty of 1967 was formulated long before such epical discoveries were even conceivable. It primarily governs issues of territorial claim, not the profound complexities of extraterrestrial biology. New, far-sighted policies will be urgently required to meticulously protect alien ecosystems from potential contamination and exploitation, rigorously ensuring that any future contact signifies cooperation and mutual understanding rather than thoughtless consumption. For the first time, the burgeoning field of space law may be compelled to formally recognize the inherent rights of life itself, however small, however unfamiliar, or however alien it may appear. Beyond the formal frameworks of law and science, this relentless search will fundamentally reshape how human civilization perceives itself within the vast cosmic drama. For millennia, humanity has predominantly envisioned the cosmos as a grand, impersonal stage for human progress, a boundless emptiness patiently awaiting our exploration and eventual colonization. But as the compelling evidence accumulates that life exists elsewhere, that narrative undergoes a profound metamorphosis. The universe transforms from a mere passive backdrop into a vibrant interconnected community, a sprawling network of living worlds, each meticulously shaped by the very same fundamental forces that shaped our own unique genesis. Our collective purpose may gracefully shift from aggressive conquest to empathetic connection, from relentless expansion to profound preservation. Children born in the coming decades will grow up immersed in the profound knowledge that the night sky is not a silent, empty canvas. Every shimmering star they behold could potentially host its own oceans, its own dynamic atmosphere, and the slow, rhythmic pulse of biology. Their cognitive maps of the cosmos will no longer terminate at the familiar boundaries of our solar system, but will naturally extend into a living, breathing galaxy. The profound question that has defined generations, are we alone, will gradually fade into the annals of history, to be replaced by a new, more expansive one. How do we fit within this greater interconnected web of life? For now, the monumental work continues quietly, diligently. Each new observation, each precisely recorded data point, adds another vital line to the unfolding cosmic story. Each new mission extends our scientific reach, pushing the boundaries of our perception. The data will accumulate relentlessly until undeniable patterns emerge that no rational mind can possibly refute. And somewhere beyond those intricate numbers, in the faint enduring glow of distant red stars and deep alien oceans, we will finally perceive ourselves not as isolated observers gazing upon a detached spectacle, but as active participants in the same universal process of life's eternal unfolding. K2-18b was merely the first to whisper its secrets. Many others will inevitably follow. Each new revelation will serve as a poignant reminder that life is not a singular, improbable miracle, but rather a recurring fundamental theme woven into the very language of the cosmos. The telescopes we meticulously build next will not merely peer deeper into the abyss, they will learn to listen with a newfound acuity, finely tuned to the faint harmonious melodies of living chemistry resonating across the vast expanses of space and time. The future of cosmic discovery will not be measured solely in miles traversed or even in light years spanned, but in the profound expansion of our understanding, in how deeply we grasp the fundamental continuity and shared heritage between our Earth and everything that lies beyond it. And when the next faint signal arrives, when another distant world joins the growing, vibrant list of the living, we will recognize it instantly, intuitively, because we will have finally learned to read the subtle signs, not as distant, detached wonders, but as intimate reflections of a shared universal origin. The search, in its deepest philosophical sense, will never truly conclude. Each profound answer will inevitably open another, even grander horizon of inquiry. Each monumental discovery will birth another set of tantalizing questions. But this, in its very essence, is what exploration truly signifies, not ultimately reaching the definitive end of the unknown, but rather perpetually expanding the very boundaries of what it includes. And in that relentless, exhilarating expansion, we begin to glimpse the real future, a human civilization that perceives itself not as the solitary centre of the universe, but as an integral, interconnected part of its vibrant living edge. In the final reckoning, true discovery often feels less like a sudden, blinding revelation, and more like a profound, intuitive recognition, a distant, resonant echo of something we, perhaps, unconsciously knew all along. For centuries we gazed into the night sky, consumed by the haunting question of who might be out there. Now, as our perception expands, we look up and realize with a quiet humility that they were always there. We simply had not yet learned the intricate art of how to truly listen. The light from K2-18b commenced its epic journey through the cosmos long before any of us drew our first breath. It traversed the immense, silent gulf of interstellar space, while humanity was still awkwardly learning to lift itself from the ground, carrying within its ephemeral photons the faint yet unmistakable trace of alien air, alien water, and alien breath. When it finally graced us with its arrival, it irrevocably changed what it means to be human. We once harboured the profound belief that the universe was silent and utterly empty, a vast, indifferent expanse awaiting our conquest or our scientific explanation. But Webb, with its golden eyes, has unequivocally shown us that silence can be profoundly deceptive. The universe is not mute. It speaks in the intricate language of chemistry, in the perpetually shifting ratios of gas and light, in the subtle yet persistent patterns that whisper of balance and renewal. Life, it turns out, is not an anomaly, not an improbable cosmic accident. It is, in its profound essence, a natural, almost inevitable way for the cosmos to perceive and comprehend itself. That profound realization reshapes everything. It instructs us that the perceived boundary between us and them, between our familiar Earth and the boundless elsewhere, is far thinner, far more porous than we ever dared to imagine. The very same fundamental processes that gave rise to microscopic plankton in our terrestrial oceans may be diligently at work beneath a distant red sun in the constellation of Leo. The identical laws of physics that sculpted the air we breathe now shape the colossal, hydrogen-rich clouds above alien seas. For the very first time, our advanced technology has transcended mere instrumental observation to attain a kind of cosmic empathy, an unprecedented ability to sense the subtle existence of something living without ever physically touching it. We are painstakingly learning to understand life not by witnessing its physical movement or observing its growth, but by discerning its intrinsic metabolic rhythm encoded within the faint ancient light of distant stars. there will undoubtedly be many more discoveries, many more signals, some exquisitely clear, others shrouded in tantalizing uncertainty. Each new revelation will serve as a powerful reminder that we are but a minuscule, yet integral, part of a much wider, grander cosmic story. A story not of profound isolation, but of deep, intricate connection. And each time a new world gracefully unveils its unique chemistry, it will feel a little less foreign, a little less alien, and a little more profoundly like home. One day, centuries into the future, intrepid human explorers will stand upon the crimson shores of other worlds. They will gaze upon skies coloured by unfamiliar suns, upon oceans that have never known the gravitational embrace of our moon, upon majestic mountains that rose into being without the shaping force of our terrestrial gravity. But in those breathtaking alien landscapes, they will find something profoundly familiar, the unmistakable, elegant logic of life adapting, persevering, and ultimately thriving. And when they finally cast their gaze backward, towards the faint shimmering blue point of Earth, they will intuitively understand what Webb began. That the ultimate search for life was never truly about finding others. It was, in its deepest philosophical sense, about profoundly understanding ourselves. Because in every spectrum, every intricate equation, every single photon that fearlessly traverses the cosmic void, there is a shared, universal truth. Life is not fragile. It is persistently tenacious. It is boundlessly creative. It is, without question, the universe's most eloquent and enduring form of continuity. The very first breath on K2-18b, the primordial molecule that first learned to replicate and perpetuate itself under a gentle red sun, may well have been a distant echo of the very same fundamental principle that shaped our own existence. Different chemistry, perhaps, but the identical timeless idea: survival, adaptation, emergent awareness. When that ancient light finally reached Webb's golden mirrors, it completed a profound circle, billions of years in the making, the cosmos, in its infinite majesty, observing itself through the discerning eyes of one of its own intricate creations. That, in its profoundest sense, is what makes this moment transcend mere discovery. It is a cosmic reunion. The stars are no longer distant, indifferent points of light. They are in a new, profound way familiar, not because we have journeyed to them, but because we now intrinsically know they are alive. And so, the search will continue, not driven by a primal loneliness, but by an expansive, profound kinship. Every telescope, every ambitious mission, every meticulous experiment will add another haunting note to the same quiet, unifying melody that intricately connects all living things across the vast, resonant expanse of existence. The universe, it turns out, was never empty. It was waiting for something that could finally see and wonder and at long last truly understand